Hello, welcome to this video session on lean operations and analytics. Previously, we learned that operations strategy looks at how you build up your own internal capabilities and performance and various abilities like inside the factory, right? And your business strategy is the outward facing part. How do you know, plan to reach out to your customers, and of course they interact with each other. And today our session is going to expand on the insight part, right? So process very much is the rendition of the operations strategy. On the inside, how good your process is like how good your body performs. Remember, we were saying the analogy of uh, an operation being like the living operation that everyone is carrying out in order to be healthy and living and even studying, which is a higher level function. One has to have a healthy body. All right, you don't have to have an athletic body, but you have to have a healthy body. How to have a healthy body? Well, all the internal attributes have to be good, right? Not too much, not too little. So you're going to eat well and all that. So it's the same for a factory to build up the healthy process, right? So it's only with healthy process that you achieve a performance and thereby be able to first complete or achieve your operational strategic goals, and then either support directly or accomplish the business strategic goals. So process very much is like our building up our health, right? How do we do that? And our agenda today is very simple, just 3 points. We look at what is the process. Some of you have done process analysis, process operations, business operations, and you might have already studied that. So we do a quick review, plus for me to point out the essential parts that connect to where it is being lean or not. Then we look at Little's Law, right, or review for you if you have done that. So we look at Little's Law, and then finally the effects of setup and batching. So when we have setup time and when we have a batch, that means a group of items to be processed, right? So how would that affect our entire operations and the entire process? So what I have for you here is a very simple minded, very simplistic illustration of a factory's process uh, that produces one thing only, right? I mean, of course, modern factories, they produce different items. Remember what we mean by different things, because even different sizing, different packaging is considered a different product, right? Because you may want to buy a drink, let's say Coca-Cola, you may want a plastic bottle with a cap so that you can drink a bit at a time, or you may prefer to buy the metal can type because maybe you have no choice because it's the vending machine, right? So uh, different demand quantities will be imposed on the different packaging due to different packaging because they provide different value to the customer like you, yourself, and myself. So here we have a very simplistic process that produces only one kind of product, right? So uh, I typically like to think of this product as a bread so that the raw material the dough, right, the flour mixed with water and yeast, is put through molding, put it in shape, like kind of force it into some kind of a regular shape. So you need a machine or people, right? Then there is baking, then there is packaging. So baking makes it edible, and then packaging makes it sellable, right? Okay, so this is a simple idea, simple, really simple. I'm not a baker, but really simple 3 steps, and then I get the bread ready for sale. Huh? So 3 steps. Now, notice that in drawing this process, the item, the initial raw material, changes in shape, right? Yeah. So the whole idea of a process is that it is a, let's just kind of give it a simple description, a connected sequence of resources, a sequence of resources. Resources are these orange boxes, right? each of which value adds to the flow unit. So technically we call it the term flow unit. Flow unit is that thing, that one thing, that instance that goes on the conveyor belt. Now I would use conveyor belt most of the time, right? Because it's familiar, but modern processors need not have the physical conveyor belt, but maybe workers to move one place to another. A small bakery shop might actually have a tray that has wheels that will move from one the inside kitchen to the outside store, something like that. So conveyor belt, right? So that's just conveying, moving the flow units from the upstream to the downstream. So far, so good, right? So the blue arrow shows the flow of the goods. They're not physically there. They're just showing the direction of the goods flowing from left to right. And of course, the flow unit will be value added at each step of the resource. So the resource, the orange rectangles here, the resource is sort of again a technical term, but it doesn't have to mean machine, doesn't have to mean people. It can be a team of people, grouping of man and machine. So here I illustrate with a machine that has or that requires two workers to operate. So the next step, baking, maybe is a very simple thing. So there's an oven and just one worker to put it in, wait for the time, and then take it out, right? And then packaging, it's done by a very fast machine, and so one worker to supervise in case it jams, and that's all, right? So it's a man machine, machine only, or group of workers can form a resource. So please, when you calculate, please don't mistake a resource as one worker. So in tests and quizzes, sometimes they will start describing two workers are needed in molding stage. And then some students will think that there are two resources in molding, so they call it molding one, molding two, and that's wrong, because here we are analyzing the process, right? So we need to describe the logical components, right? The resources correctly relative to the context of this process. So there are a few numbers that you see, right? So the flow of goods go from left to right, but let's finish off with also the other arrows. Once it goes out of the factory, these are the completed items. Need to move myself away a little bit on the right side, yeah? So these are the completed items. They are ready for sale. My pointer should show this. Okay, easier to see. So these are completed items, and they go downwards towards fulfilling demand. So there's a big aim written on the bottom left. The whole aim, the whole idea of all these charts and processes and whatnot is to match, if not perfectly, then to better match supply with demand. Supply, we hear this all the time in economics and whatnot, right? We match supply with demand. That's easier said than done, because supply is what we control, our business controls, right? We want to supply more, supply less, supply faster, supply slower. Demand is out of our control. Who controls it? Right, the customers control it. And the customers don't know. When we say customers, we're talking about the collective, separate individuals and businesses, right? So they don't talk to each other. Hey, you want more bread, is it? So let's buy more bread. They don't collude, right? So they behave more like a herd, and individually they think on their own, they fulfill their own needs, but then collectively there's a stronger demand, a weaker demand. While that can be described or even predicted somewhat successfully by statistics, it's uncertain. So it's kind of more like generated by customers. And so to match our supply with demand is a tough thing. And there are a lot of theories developed to try to do that. Not often successfully, but there are times when we are able to narrow the gap, and that's good. That's achievement, right? So theories like forecasting, right? Theories like studies of consumer behaviors, economics, macro, microeconomics, and so on and so forth. They feed into the understanding of the supply and demand at that particular geographical location or at that particular time. So, for example, before tariff war, right? Before tariff war, before U.S.-China tension, supply demand is like that. After the tension, it will be another way, and after tariff war, it will be all the way suppressed or all the way increased, right? And can we are observing all these at the point in time now. And okay, so the demand is once it goes out of the factory is beyond our control. So we have these numbers, and I'll come to those numbers in a while, right? While discussing all the terms and how they relate to each other, right? And so at this point in time, we see that there is also the flow of money, of course, because customers will exchange their hard-earned money with your product, right? So flow of dollars all the way back, yeah, they channel backwards. Of course, we don't literally pay the packaging guy some money, a lot of money, and then we pay, and then, so baking will collect a bit and then pass on upstream. It doesn't literally happen that way, but we can think of it that way, all right? Because the sales guys for the company will collect the money or will complete the sales, and then the payment will go to the company's bank account. The accountants will start attributing the expenses, right, to individual stations, or the operations manager will do this job. So the flow of money goes upwards, upstream. Yeah, and the flow of information is one important thing that you might be learning or that you realize now, because typically we understand that you make goods, we buy, customers buy by paying money, but we seldom, unless you're on the inside, we seldom would see this double arrow flow, which means it is very necessary, very healthy, right? Very important for information to flow forwards and backwards. Okay, so because if not, then it will be like, three separate resources operating on its own, disconnected from each other. While physically there's a conveyor belt connecting them together, you've got to have the brains to connect together. That is the inflow of information must permeate through, right? So this double arrow is an important component that this chart is highlighting, this slide is highlighting, that if you have a single arrow, either left to right or right to left, it's probably not a very healthy process, and you want to make sure there's double flow of arrow. So in subsequent lessons, we'll talk more about what this information is about, right? So how the information flows. Right now, we have talked about all the arrows, okay? And then I want to talk about, of course, this big encirclement of this part. This is the factory. This is what we can control. And I like you to, of course, always keep in mind, right? So you might understand, but you might have forgotten for a moment, and then that's where you may misunderstand some of the terms, some of the calculations, some of the numbers. So keep in mind all the time about who owns that number or that terminology. Who owns that or who controls that? Very important. For example, we already talked about demand, right? Demand is not say controlled, but generated, right? Or it's okay, fine. If we just abuse the word a little bit, it's controlled by customers. Supply is controlled by us, the business. So whenever I'm describing, I'm talking about us as in the owner of the factory. We are the factory. We own the factory. So and because we control the supply, and somebody else, the customers, control or generate the numbers for the demand. It's always a cat and mouse chase, right? Yeah, I try to match my supply with the demand, and I always don't know what you're thinking. So I always anticipate, and I always over anticipate or under supply, right? So therefore resulting in losses. And so as a business, I want to match my production supply with the right level of demand for the consumption. If I oversupply, of course, they'll be discarded, right? And that will be losses borne by me because nobody is buying up those goods that nobody wants. If I undersupply, then I am stepping on my own feet, right? Because I have more demand that I don't have goods to sell and convert into profit. So both cases are no good. Therefore, exact supply equals demand is what we are trying to achieve. By what? By having the double arrow flow of information so that we are smarter, wiser. We are always also, as much as possible, in real time, uh, sustaining this equivalence, this supply equals to demand principle. Why I say that is because as time passes, momentarily you may have supply equals to demand. Then after that, supply exceeds demand by more and more and more, right? So then that will be disastrous. As time passes, supply becomes lesser and lesser and lesser because we didn't produce fast enough. We didn't know that demand has started to increase by a lot, right? Like gold. So gold recently shoots up, and of course it's not that if you want to produce more, you produce more. You just cannot produce more, right? So if your production, your supply is limited, is constricted, and demand increases, then what happens? Price increases. And that's more economics. What I'm saying that then the supply doesn't match demand, right? So the only way out, higher prices, just to deter others from buying or having the ability to buy. So of course that's gold, which we don't need. But then if it is about rice, about essentials, about water production, we have a big trouble when we don't match supply with demand. Yeah. Okay. So next, I want to kind of talk about some of the numbers here. There are two colors that I carefully picked. The black colors describe the attributes. They are static. The attributes of the resources. In this case, the molding machine. So this particular machine is capable of or has a capacity of producing at the maximum 3 pieces per minute. Is that okay? All right. So capacity, another technical term. Capacity is the maximum flow rate that the resource can handle. Of course, all these are stated in the next slide here. Okay. Next 2 slides, basically. Right. So the resource capacity is going to be the maximum flow rate of the resource. So every resource has a number. It's just like everyone has a number in terms of ability to solve lean operations exercise questions. Right? How many questions can you solve on average per hour? 4? Okay, that's yours. Oh, you are better. 6 questions. Good, nice, right? So no, for me it's 1. I can only do 1 question per hour. So, but then with practice, with training, I can upgrade myself so that I can solve faster and faster. And that, of course, is every student's goal, right? Throughout the semester to increase your capacity, your resource capacity, to be able to solve more questions, a higher rate of question solving per hour or per minute. So notice that it's like a speed, or rather the maximum speed on the odometer, speedometer. How fast at the maximum, how fast can this car run? 200 kilometers per hour, 240 kilometers per hour. So that's the equivalent idea, right? Capacity. What's your maximum flow rate? And what is flow rate then? Flow rate then is, of course, the current speed, right? The current rate of flow of the flow units. Remember flow units? I try to call it fun. Okay, so every unit, every instance, right, is flowing on the conveyor belt. Okay, and the reason why the conveyor belt cannot go faster is because if it's too fast, then it will if it feeds flow units at too fast a speed, then the machine or one of the machines or some of the machines will jam. So it can only flow as fast as the lowest capacity resource in the entire process. So flow rate is the prevailing flow. prevailing flow rate of flow of the flow units. Okay, so flow rate is always less than or equal to C, the resource capacity. Of course, you get the idea, right? Less than or equal to. So in solving problems, sometimes tests and quizzes, their questions might not describe the current flow rate. So here I do describe the current flow rate. I'm saying the FR in is 1 piece per minute. The FR out is 1 piece per minute. It's a speed, right? So it's a count per minute. Some questions, they don't talk about the current flow rate. They just say molding machine has 3 pieces per minute, has a capacity of this. Baking has 2 pieces per minute. Packaging has 6 pieces per minute. Then how do you proceed to calculate? Because you definitely need FR. At this point in time, you will assume that the flow rate is the process capacity. Notice the difference. I talked about resource capacity, and then there is a process capacity. Process means the entire strung up resources. It means the whole factory, the whole factory. So think of process means the factory kind of thing. So process capacity is the highest flow rate that the lowest capacity resource can take, right? Yeah, so which means it's the same as the capacity of the smallest C for all the resources. So in this case, 3, 2, 6. So baking is going to be the process capacity. In other words, the maximum rate of feeding of units into this whole factory, whole process, is as high as the lowest of all the resource capacities, correct? Yeah, because that's the maximum I can feed. Think of ourselves. We have a mouth, we have a throat, right? And then we have stomach. Let's say that's all. So how fast can we feed hamburgers or sausages or rice into our mouth or into our system? Well, it's the fastest that these 3 resources can process by flowing through them, right? So our mouth can chew and digest or swallow at quickest rate 3 burgers per minute. Our throat can take because it's narrower 2 burgers per minute, and our stomach a bit more capacity, so 6 pieces per minute. But how fast can our body take as a whole? Well, no faster than the narrowest channel, right? Because if you try to swallow more than what your throat can handle, you will choke, and your whole body goes into convulsion. The whole factory goes into kind of a damaged state. All makes sense, right? Yeah. So anytime you're not very sure, you kind of like can put the analogy onto your own self, because you know yourself, right? And you can say, would that work? No, I'm going to choke, right? So the fastest rate of flow of burgers through our mouth, our system, is the lowest capacity of our organs, right? So the mouth, the throat, and the stomach. Yeah, so that's exactly what this is all about. And of course, I don't want to go through individual items as I talk about the picture, because it's easier to look at the picture. I can just point at some of these things, right? So process capacity, that's kind of related to resource capacity, but not the same. Process is the overall, and it's the maximum flow rate that you can feed into the process. Yeah, but another way to look at it from the inside out is the minimum of all the resource capacity, right? So our mouth, our throat, our stomach. Which one has the lowest capacity? That is the maximum rate of feeding of burgers into our system, which is our process. And it's also equal to bottleneck capacity. What is bottleneck capacity? The capacity of the resource that is forming the bottleneck. So bottleneck is that thing, that resource. Bottleneck capacity is that resource which is choking the entire process, which is having the lowest capacity. So bottleneck is that resource, not a number. It's that thing, that machine. So bottleneck is that machine. In our case, it's the baking machine. What is the bottleneck capacity? We look at the capacity of the baking machine. Okay. In tests and quizzes, the test question will tell you this. Oh, the capacity of the baking machine is 2 pieces per minute, right? But in real life, where do we look? I tend to look at this capacity as machine label. Why? Because we have to then turn the machine around and look at the back. There will always be a label, and of course, that's just virtually speaking. Some machines will have that capacity stated in the manual, right? So yeah, but that label, that machine label, is going to say that this machine was engineered, was designed, was produced with a maximum capacity of 2 per minute. Right? You can keep running at 2 per minute and you'll be okay, safe, and baking good baking or baked breads. But if you try to feed faster, right, then you run into some trouble. So that's the resource capacity. So resource capacity, there is no calculation. It's kind of coming with the resource itself. Yeah. Of course, for human, when I say what's your resource capacity for solving lean operations problems, for humans, we can evolve, we can upgrade ourselves, right? We can we can't change ourselves to another machine, but we can upgrade ourselves to become more proficient with it so that we can kind of invisibly increase our resource capacity for that skill, for that task. Maybe at the expense of lowering capacity for other skills, other tasks. But that's beside the point. Okay, so that's the resource capacity. Now we see a little P1, P2, P3, and I put them in black. Why? Because they are tightly related to the C, the resource capacity. If your resource capacity is 3 per minute, your processing time, P, per flow unit. That means each flow unit on average. Here the stress is on average. Don't look at the individual. So here in the factory setting, the individual processing time, the individual flow unit, might have longer, shorter processing time slightly, but the average is pretty much covering 90%, 99%, right, all the time. So the processing time per unit is going to be the reciprocal of the capacity. So that means 1/3 flow unit, 1/3 minutes per piece. So if you convert that into seconds times 60, you get 20 seconds. It's just a reciprocal. Oh, does it make sense? If I can bake 2 dough per minute, then each dough, how long do I take to bake? Well, 30 seconds, right? Because you divide a minute by 2. So the reciprocal of C. And same thing here, 10 seconds. So that's what is giving rise to this formula. And this formula is tight, must always be respected. So in other words, in some test questions, quizzes, they might tell you that the processing time for packaging, all right, is 10 seconds. And they don't even need to tell you processing time for one flow unit. That is automatic, right? So the processing time is 10 seconds. So what's the capacity? Oh, well, that's just reciprocal of the processing time. So 6 pieces per minute, converting the time. Okay, so very tight relationship. I tell you one number, it implies you know the other number. And of course, that's how we test you. So it implies that you know the other number right away, immediately. Okay, processing time is fixed so long as resource capacity is fixed, right? Now, processing time is fixed even if you feed the flow rate in at a lower than capacity rate. Do you follow? Okay. Maximum rate I can feed the whole process is 2 per minute, because if I feed 3 per minute, molding will have no problem, baking will choke, and then of course packaging will receive nothing, right? Everything will be jammed. So I can feed at 2 maximum. But can I feed at 1 per minute? Of course, right? Let's think of a car. Maximally, you can run at 200 kilometers per hour. Can you run at 100 kilometers per hour? Of course, right? So I can feed this. Now, every piece that I feed in, how long does it take for the molding machine to process? 20 seconds, correct. not 1 minute. 1 minute is the time gap between the consecutive flow units. That's the cycle time that we are talking about. Okay, so the time gap between consecutive flow units is called the cycle time. And that, interestingly, has a reciprocal relationship with the flow rate. So if you feed at 1 piece per minute, you feed 1 piece per minute, and if you watch the time axis, right, after 1 minute, you feed again. What's the time gap between the two consecutive units? 1 minute. 1 minute, right? So that's the cycle time, CT. So far, so good. But then, when that piece enters molding, how long does it take for it to be molded? Not 1 minute, of course not, right? It takes 20 seconds. So this is the part that is like a little bit, making the whole calculation a little bit more, I don't want to say difficult, it's not difficult, it's just a little bit trickier, right? Because it's like, I thought capacity is maximum, right? Maximum. But then if you feed at lower than maximum, like 1 out of 3, right? Just barely 30% of my ability. How come the processing time is same, but it is supposed to be the same? It is treated as the same. It is also in real life the same. That's how fast or how slow molding machine does to the flow unit, right? So that's 20 seconds. So keep in mind this part, right? That while processing time for the resource is reciprocal, tight relationship with the resources capacity, which is maximum flow rate, the processing time is applicable to each and every flow unit, even when the feeding rate is way lower than your resources maximum capacity. Okay, so same thing here. When it goes into baking, baking takes a long time, right, per flow unit, and packaging takes a relatively short time, 10 seconds. So these are applied to each and every flow unit, while consecutively, right, the feeding rate is a slow going operation, right, that has 1 minute apart. So as we lower and lower the flow rate in, the cycle time lengthens because it's, reciprocal relationship. So much so that if you feed only 1 piece per hour, right, then after 1 piece you wait for 1 whole hour before you feed another one. Will the resources have time to finish that 1 piece? Of course, right or not? They are like so underutilized. And that brings us to utilization. So if we feed at 1 piece per minute, the very capable machine like packaging will like, oh, come on, can you give me more work, right? If they were human and can speak, then they will be saying, I'm so underutilized, I can do more, can you give me more, right? And of course, if you are paid, right, if packaging is a human worker and you are paid on a per job, per flow unit basis, then you want more. You don't want to be restricted by a bottleneck upstream, right? So that's, yeah, often also giving rise to disputes in some of these situations, like, wet market. They hire workers to maybe pre-process the fishes, those small fishes, ikan kuning and all that stuff, right? So they want to chop off the head and the tail, right? So chop off head, chop off tail. It's a very simple thing. But if you don't chop off head, chop off tail, you, you are going to increase the weight or whatnot, right? So they want to pre-process. So typically they might be paid on a per fish basis. So that worker, not having studied all these, will be very keenly aware of the need for more fishes to be fed to him so he can chop off more head and more tails and then be able to collect more money. So it all comes automatically. But the reason why we want to quantify them is that we're able to more precisely pinpoint, some of the critical issues like bottleneck, right? And also we have some more discussions about how to treat bottleneck, right? So back to our discussion here. So just like processing time is reciprocal relationship with resource capacity, cycle time is having reciprocal relationship with flow rate. And the lower the flow rate, the lower the utilization. The higher the capacity, the resource capacity, the lower the utilization. No, there are two kinds of utilization. Resource utilization and the process utilization. Just like capacity. But fortunately, the calculation is also similar to capacity in the sense that constant flow rate, right? So 1 piece per minute. The utilization for molding is divided by the resource capacity, or rather the resource utilization is defined by flow rate over the resource capacity. So for molding, it's 33%, right? For baking, it's 1/2, so 50%. I'm 50% busy. And for packaging, it's 1/6. How much is that? 60.7% busy, even lower, right? It's because I'm very capable, and you're feeding me at a very slow rate. So I'm like very totally not heavily utilized. So how do they look? How do they behave between a heavily utilized resource and an underutilized resource in real life, right? So calculation we know, right? Baking is 50% busy, like quite very busy. Packaging is 17% busy, not very busy. So how do they look like? Well, baking will look very busy, literally, right? So a lot of activities, a lot of movements. If it's machine, there will be baking, catching, right? Moving relatively more frequently. If it's worker, then the worker will be having a lot of activities. You know, the hand might be swinging very quickly and whatnot, right? But for packaging, it will be sluggish. It will look sluggish. It will look like the activities are very uh, not very enthusiastic, uh, a lot slower in terms of movements. And what happens when packaging is done with the flow unit? The worker or the machine idles. Okay, so we use the word idle on the resource, be worker or the machine. So idle time is a technical term, right? So we describe the resource as having idle time whenever it is not processing. So processing is 10 seconds, right? From unit to unit, what's the time gap? You know, that's the cycle time. So from unit to unit, the time gap is basically 1 minute, right? So at those times, I'm not processing. For a whole 50 seconds, I'm not doing anything. I'm idling, right? So I'll be like just fixed, locked, right? And not doing it. So that's called idle time. Idle time, yes, it's not value adding because I'm not doing anything to help my potential customer, right? At least when I'm processing, I'm value adding. I'm making the bread look nicer with a packaging. So increasing the value of the bread. Therefore, my customers will like it more and buy it. So there's value, right? There's emotional value, whatever it is, or genuine value, right? Like certification value, right? Hey, you know, by packaging with a stamp of the company, this is a certified healthy brand, right? So that's why it increases the trust of the customer, and there's value. So for the rest of the 50 seconds, I'm not doing anything to help my customer. So I wasted, right? That 50 seconds is the invisible waste. We all understand that idling is no good, but usually our sense of not having and adding value kind of situation is or arises from the ROI, you know, from financial perspective. Like, hey, you know, I bought an expensive machine and it's idling. We should make it work more. You know, that's from the financial perspective. But from lean perspective, we are saying that's bad. It's a waste. Remember waste? We talk so much about waste, right? It's a waste. Idling time is waste. Why are you making this worker, this machine, idle? When we look at a machine, right, that is sitting there not moving, anyone, worker or manager, will kind of shake their head and say, what a white elephant, right? Because we all understand that you put in money, you bought a heavy duty machine just for it to idle is bad. That's from a financial perspective. When it's worker, we tend to say, who is managing this worker? How come so bad? Or why is this worker idling, right? And when you have so much work to do, no, you're not feeding me fast enough, right? So it's a systemic problem, and we tend not to think of ROI for worker resource. But for lean, we're treating it as just the same. You make machine idle, that's a waste. You make worker idle, that's a waste. Don't generate waste. That's no good. You're not value adding. That's the perspective that lean teaches us. The same physical phenomenon, idling resource, but different perspective that lean injects in us to help us see from another view that, hey, whether it's worker or machine, no good. Okay. All right. So these blue color printouts, they are talking about a dynamic kind of parameters. That means as the process is being executed, let's make it run. Let's turn it alive, right? And we turn it alive at a rate of 1 piece per minute. That's the blue color part. So the blue color part can change, but the black color part is fixed. Now because processing time is tied to the capacity, resource capacity. Resource capacity is machine label. Machine label cannot be changed. So it cannot be changed unless you change the machine. So it's like your own resource capacity for solving lean operations exercise questions cannot be changed unless you practice and upgrade yourself. You spend the time to upgrade yourself, right? But if you do nothing, then it is more like a fixed number. Right? So here the blue numbers, the blue colors are also expressing something that is external, like FR out. FR out, we sort of pipe it outwards. So to the external environment, we are ejecting an FR out of 1 piece per minute, right? Because FR out cannot be more than FR in, and therefore it's a number that's influenced by the real-time environment, the outside of the whole process. So FR out cannot be more than FR in. You all understand that, right? You cannot be producing more breads than the fed in raw dough. There is a situation when we have FR out equal to FR in. Okay, we are like ignoring all the defects and debris, whatever it is, all the minor losses here and there that it will inevitably be generated by a real life factory or process. But we are assuming FR out equals to FR in. That assumption is called steady state equilibrium. So when FR out equals to FR in, what goes in at that rate comes out at the same rate. Steady state equilibrium has been attained. That's the way we think about it. So the technical term is called steady state equilibrium. And what's so special about it? It's like a long garden hose. Yeah, you connect one end to the tap, and then it starts to wind and wind and wind, like 10 meters long, right? So at first it's empty, and you have 0 FR in water, FR in 0, 0 liters per minute. FR out, water coming out from the other end, 0 liters per minute. Steady state equilibrium, right? It will sustain. But then when you turn on the tap in full force very rapidly, let's say the maximum is 5 liters per minute, right? So 5 liters per minute starts to gush into the inlet of the hose. Do you immediately see 5 liters per minute coming out? No, right? There will be this few seconds, if not even like 1 minute of excitement and tension that you are keenly expecting the water to suddenly, spill out from the other exit of the hose. That travel time of that gushing water, right? You can see the whole pipe, the whole hose starting to dance because the water is gushing through with a lot of force, right? You have FR in 5 liters per minute, FR out 0 for that 1 whole minute. Yeah, and that 1 whole minute is not in steady state equilibrium. But will it reach steady state equilibrium again? Yes, right? We wait for 1 minute, the frontal frontier, not efficiency frontier, the water frontier, right, in the gushing water, right, will take 1 minute to traverse through the 10-meter hose, and finally when it comes out, 5 liters per minute. Correct? Because no water loss throughout the hose. So now FR in 5 liters per minute, FR out 5 meters per minute, we have again attained steady state equilibrium. Right? So here, same thing, although not in a dramatic manner as water gushing through the hose, but we are feeding in 1 piece per minute. At the start of the factory of the day, nothing is inside, right? So FR in, 1 piece per minute. If you look at FR out, nothing. So if the time to travel through the factory is, let's say, 1 hour, so for 1 whole hour, we're not in steady state equilibrium. So we have to wait until 1 hour is over. When the first entity goes through everything, of course, subsequent entities also will follow through, right? And then FR out starts to sustain a 1 piece per minute rate. Then we say that we have regained the steady state equilibrium. So far, so good. Yeah. So all our calculations must be based on the assumption that FR in equals to FR out. Okay, so none of the formulas and discussions we talked about will work if we don't have steady state equilibrium. Okay, from here, the FR out will go through a lot of market mechanics, right? Like distribution, lorry, trucks, and whatnot, and to finally reach the market. And here we put a FR demand as 1 piece per minute. The FR demand is the estimate of the average consumption rate. If you're selling bread, then the average rate that your bread flies off the shelf, bought by consumers. If the consumers eat, good. If they throw it away, you got the money, right? So the money did flow back, isn't it? So they did want to buy, except maybe last minute they decide not to eat it, or they misplace it so they cannot eat it. So fine, but then the money was compensated back to you, so that's part of the demand. So the demand, the FR demand, is the consumption rate, right? It's the digestion rate of your product. So 1 piece per minute. Of course, right, what I put here is a very ideal case. The demand, FR out and FR demand, they are the same. FR out is our supply. FR demand is our rate of demand. So now we can quantify these two very generic macro terms. Did we achieve supply equals to demand? Well, in this case, like a very ideal and theoretical case, yes, right? But as you can imagine, the FR demand will have fluctuations, much more than our FR out. Yeah, because we are a factory, we are business. Business tend not to want to receive or generate fluctuations. You want planning. Planning, if it is varying a lot, then how do you plan, right? So whatever you plan instantly gets outdated. So we don't want to generate fluctuations for our FR out. But FR demand will always carry a lot of fluctuations. So here, let's just simplify everything. We say that FR out equals to FR demand. And here we see a TT, which of course suggests something similar to CT, cycle time. The TT is called the Takt time, T-A-K-T. So this is a German word, right? So Takt time. Long story short, it is the reciprocal of FR demand, which means same relationship as cycle time is to FR in. So FR demand is the ultimate, right? Not FR out. Not FR out. Okay. So FR, that's a common mistake by students. FR out has the same number as FR demand because in tests and quizzes, they want to simplify the complex situations existing in real life. So they just say, oh, factory is meeting demand, right? So FR out has the same number as FR demand. But then they are very different because remember, we control FR out, but customer controls FR demand. Therefore, duct time being having a mathematical relationship with FR demand, the reciprocal of FR demand, is also controlled by the customers, not us. Okay, cycle time is having a reciprocal relationship with FR in. FR in here sometimes here this part in real life is getting a bit crazy. The FR in, do we control FR in? Yeah, in certain factories, yes, because we buy the raw materials, we feed it in, right? So of course we can tell the worker, we can fix the machine to produce an FR in of 1 piece per minute. So we control. But there are times when, for example, and it's not just restricted to this, but for example, agricultural harvesting, right? So you may grow the rice field, you may grow the apple trees, you may, try to grow. But due to weather, due to sudden change in, the weather behavior and climate and seasons, maybe sun flares, sunbursts, and typhoons and whatnot, your harvest, which represents our factory's FR in, right? Because we harvest, then we process the rice. We harvest the apples, then we process the apples. So our FR in is the harvesting. The harvesting may not result in 1 piece per minute, right? It may be 0.2 piece per minute. It can be a lot lesser, cannot be a lot more, right? But sometimes, yes. Sometimes, in Brazil, for example, the weather has been super nice and end up they have super high harvesting or something like that. But more because they initially thought there's some attrition, right? They planted 100%, they thought they can harvest 80%, due to some losses in harvesting. But then whether everything turned out to be good, harvesting was smooth, so they end up getting 99%. All right, so that's why it's like, wow, super good harvesting. So the corn prices dropped and they throw away the corns just to make sure, just to reduce the FR in, right? Just to make sure that it's rarer, so the price is higher. That's a different story. That's economics, right? But we are talking about FR in not being in control. So it's controlled by the weather. And that's just one example. One example, right? And then of course there are times when FR in is due to forecast. Okay, if the forecast of demand is high, then we try to produce more by having higher FR in. So we fix it due to our forecast of the FR demand. So in this case, it's like both, right? It's like it's also anticipated demand. That's why we fix the FR in to be higher. So we kind of like we control, but we are controlled by the anticipation of something we don't control, right? So that part is again a mix. But that's just to highlight the importance of knowing whether you have total control of numbers or not. So FR in is a little bit interesting. FR out definitely comes from our controlled production. FR demand is beyond our control. So duct time is the time gap between consecutive products from us being consumed. So like if you think of a cartoonish situation, our breads, our packaged breads are all laid out on the shelf of the bakery. We stand there and watch, right? When one of our bread is being bought, we start the timer and we keep it running until the next customer randomly comes by. Okay, I want this bread. Hey, that's from us, right? So then we stop the stopwatch. That time gap between two consecutive products that are being bought or consumed by the consumer is the takt time. Is the takt time. In solving problems, back to classroom, in solving problems, question setter wants to reduce all the complex possibilities to a very simple case, so that we test you on the basic understanding. So takt time is just equal to cycle time. That's just like saying FR demand is the same as FR out. And because we are assuming steady state equilibrium, so FR out equals to FR in, so literally FR in equals to FR. So that's just a simplified assumption. So if that assumption is true, then takt time will of course be equal to cycle time, right? So sometimes you may be told, sorry, what's takt time? Oh, it's the same as cycle time. And that is a long story short. Long story short, right? Just to make things simple. But when you go out in the real world, you find that they are not always the same. How come I learned in theory, but yeah, that's the difference, right? Because cycle time is FR in and takt time is FR demand, rather different behavior. All right, at this point in time, I'm pretty much done with the picture here. Of course, if you have more questions, just feel free to comment below and bring it up in class. And if you look at this picture again, right, let's just see this picture there. And we want to quickly run through all this, right? Basically, I've covered them all. I don't want to re-discuss every single one. But I think I didn't pay enough attention or focus on flow time, right? Flow time is the time it takes for a particular flow unit to go from the entry to the exit of the process. So just now I said that, well, to achieve steady state equilibrium, remember that the particular unit, the first one, but it can be any one. I mark a star here. It goes through and goes through, and it took 1 hour, for example, right, to come out. Okay, so that 1 hour will be the flow time of the process, correct? Okay. Of course, we can also look at the resource. Can the resource be a process? Yeah, why not? Because we just wrap it around a simple dotted line and call that one resource process. Can, right? Of course, then a lot of terms will overlap because a resource capacity is immediately the process capacity. Yeah. So when we do that, then the flow time is time it takes for going into the process, the process and the resource, and coming out from the resource and the process. So it's just the processing time, but it's totally trivial, right? But so we don't try to do that. But in case there's such a test of questions that talk about the flow time through a resource is 20 seconds. That's just a tricky way of saying the processing time is 20 seconds, right? Because one resource, one process, nothing else. There's nowhere else for the flow unit to waste the time on except to be processed, right? So that is basically the flow time. So the flow time is the time it takes. So if you look at the study, like a 3-year degree course. So yes, you're not locked up in the university for 3 years, right? You can come up, you attend classes and you go home. But you are constantly being registered. You are always showing yourself as a student, right, of this university. So the flow time for you to become a process unit, a graduate of this university is 3 years or 4 years, whatever. Right? So flow time from entry as a raw material high school student to graduate, 4 years flow time. So that's the flow time. So long as you're inside the process. Okay, so remember that. Huh? And it has to be you, that same individual, because every year there'll be graduate. That's other people, not you, that marked flow unit, right? So a particular marked flow unit. Or you can watch your elder brother, right, who is in university now. Okay, so time it takes for him to graduate, that marked person, that person in particular entered in year 2025, and then he will graduate in year 2029. So that's a difference of 4 years. That's the flow time. Okay. What happens if you have different timings? Like some universities you can graduate in 4 years, some you can graduate in 3 years in the same university because of different courses. So what's the flow time for this university? Then you take the weighted average. Like 100 people graduate in 4 years. 100 people graduate in 3 years. So you take the weighted average, right? Because 100 and 150% each. So take the average. The flow time is 3.5 years. Okay, so that's the way we calculate. Everything, all the numbers here are essentially having a average tagged or prefix onto it. So throughput rate, throughput time. Throughput, the word throughput is just another word for FR, right? So flow. So throughput rate, flow rate. Throughput time, flow time. Synonym for flow time. FR demand, we talked about production supply rate. Lead time, right? So we spent a lot of time talking about lead time also in the previous last discussion. Lead time is between when order is placed and order is received, right? So lead time is a very important time in real life, because if it's too long relative to other competitors or suppliers, you may lose out, right? How many of you have browsed and purchased from online e-commerce stores? I'm sure most of you have, right? Whether it's buying t-shirt or watch or pen or USB drive or whatnot, right? And you will see alternative suppliers. Sometimes the prices are the same. So what you look at, right? Is there a fee charge for delivery or not? Yeah, I guess. Yeah. But let's say it's all free. Then you look at finally who delivers faster right now. So Amazon, for example, puts that up front because that is a competitive parameter that consumers like you and me look at. Yeah, because if I can deliver to you today, right, this supplier, the other one is 3 days from now or 3 months from now. You like bye. Don't you want to see that, right? So 3 days from now, you then ask yourself, can I wait for 3 days? But that same price, why do I get it now than 3 days later, right now? Yeah, so if it's same price, same delivery free charges, then you want to look at lead time right now. Lead time, the faster you can get, the better for you to satisfy your demand and your desire. So why not, right? Yeah, and so that can become a competitive advantage. So just quickly going through this, we want to say that the aim is for the supply to meet demand, right? So cycle time is our supply. We control it. Of course, I talked about exceptions just now, but generally speaking, we control. So cycle time, we decide. We try to match it to takt time, which is generated or controlled by customers. So if cycle time is shorter means we produce faster. Takt time is sluggish, very long. Your bread sold already, and it took a long time, right? The takt time before another bread is being sold, right? So demand is very slow. So if our CT is less than TT, supply is lesser than demand, then CT is lesser because CT is short, so we are producing a lot. So we are producing faster than demand. Then we are, then there's no demand, so the breads will get expired, and then of course they have to be thrown away. So waste. The other way around, CT is larger than TT. So TT is your bread goes off, right? And then very quickly your bread goes off. So it's pretty short, meaning the FR demand is high, right? Our CT is sluggish, it's long. You produce one unit, long time later you produce another unit, right? So the supply, the FR out is very low, and we are producing slower than the high demand, right? And we're not talking about customers wanting bread in general. We're talking about customers wanting your bread, this brand of bread, this model of bread, like this chicken sausage bread that you sell. They want it. Their money is there already, ready to exchange, but you don't have. Sorry, no more. Then that's quite a shame right now. We're not talking about anticipated need. We're talking about takt time really is short, right? So the demand really is high. They want it. It's known. It's not forecasted. It's not anticipated. It's known. But you're not producing it, you're not meeting, then it's a shame. And so you lose profits unnecessarily because you have the factual demand, right? So that's why uh, it's a problem. Now, it's easy for us to sit in a nice classroom and say on paper and then discuss, oh, it's a problem, just in this case, reduce cycle time, increase the supply, finish. But it's way easier said than done, because how do you just increase the reduce the cycle time, increase the production? You cannot, because it's already maxed out, right? It's already maxed out. If it's already maxed out, then the only way is to fix the bottleneck, to enhance your process capacity. How to fix? You have to upgrade the machine, right? How to upgrade the machine? You have to buy. So buying machine, and you don't buy an old one or a slower one. You buy a faster one, modern one, higher performance one. And of course, market will demand a higher money, right? Investment. So do we have the money? And by the time we finish, and because it takes time, right, to buy, to replace, to run it, to smoothen out the production process when a new um, machine is being installed. Think of it as going through a organ change operation, like I don't know, change a liver or kidney or replacement of kidney, right? So once you replace that organ, that resource, the patient, you will need some time to recover for the systems to reinteract with the newly transplanted organ to see if it's okay or not, the blood flow is okay, no rejection and all that, right? No hiccups. But it's quite similar here when we change the baking machine to a higher spec, higher performance baking machine. Will the inflow and the outflow conveyor belt, will they convey nicely and all that? Even when studies have been done earlier on. Okay, let me examine the schematics of the new model that we intend to buy. Does it work? So paper-wise it works, but when you put it on the ground, you realize that maybe the baked bread is being airdropped onto the conveyor belt, which is like 50 centimeters below. Oh, didn't batch out well. Did it fall onto the conveyor belt? Yes, but after falling, the bread breaks because it's a baked bread. It's very crispy. When it has a air gap, it drops and then it will crack and some of the breads will break and the yield becomes a lot lower, right? And so on and so forth. So a lot of things might work on paper, but when you do the running, you suffer additional hiccups and issues, not insurmountable, but then it will slow down or delay the launch, right? So just easier said than done. This is a summary here. So always keep in mind as you study through all the concepts and principles in this course that the formula is one thing, but you got to ask additional perspectives questions, right? So like, who owns it? Can it be changed? Will it change very quickly? How much money is involved in changing? Who is paying the money? Well, a lot of these questions are very interrelated, so that when we say that's just good to be increased, yeah, but how come all the businesses are very reluctant to do that immediately, quickly? Money, 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 or various other things, right? Regulations, yeah, and many, many. Okay, so lastly, I see that we have talked about the rest, right, and the inventory, right? Now, inventory is basically synonymous with work in progress. I understand this is uncomfortable, right? But work in progress is kind of used interchangeably in tests and quizzes. So please be careful about it. And WIP refers to the number of units within the process. So if we look at the picture, we say, is there inventory? Layman tends to look at the front. Oh yes, a lot of raw material, right? Or the end. Oh yes, a lot of stack up produce goods. But for lean operations, business operations, we look at the internal here. The inventory of the process. The inventory of the process is the number of flow units stuck inside the process. Stuck as in flowing with it, moving along. Okay, so they are inside the process, they are currently being conveyed on the conveyor belt, they are currently being processed. If you have a snapshot instance of the of a picture of the process, you'll find that there is, right, non-zero, some amount of some quantities of the flow units being held within the process in various stages of the processing. And that total count, right, is the inventory number that we're looking for. So in a particular test exercise or questions or quiz, you may be asked, calculate the inventory of this factory. So factory is the process. So calculate the number of half done, right, inventory that are on various stages of processing within the factory. So that's by counting and then taking the averages, or by using Little's law that we'll talk about next. And of course, the lower the inventory, the better, because inventory costs money, right? So like for Toyota, the car manufacturer, right? Their factory will be 7 football fields wide and hundreds of meters long for a car chassis to go from metal to start the engine kind of a car, drivable car, right? Road safe car. For that to go through, right? The flow time, if you remember, from this particular metal frame, right? So this metal frame to a drivable car. Let me mark this and watch. Okay? It may take 7 days. It may take 10 days. Okay, so let's say 10 days. So if it takes 10 days for it to flow through the 7 football fields before it comes out as a safe, road safe driving car, then we need to kind of estimate how many such semi-completed cars are there in the several hundred meters long processing line, right? That takes 10 days to flow through. And you will realize that, wow, suppose it's 100 for simplicity. And each car is not cheap, right? Of course, towards the later stage, the nearing end product car or flow unit will be worth more than the initial stage where it is only a chassis, right? Let's take an average. So if the average value of, you know, a flow unit anywhere on the processing pipeline is 5,000. I think that's on the lower side, huh? So $5,000 times 100. That's $500,000, right? $500,000 worth, and that's on the underside, on the conservative estimate, right? So $500,000 worth of goods flowing along, and we are not talking about other things, right? Other parts, other tools, and whatnot. So $500,000 of inventory, work in progress inventory flowing along. So if we have another way to reduce it, maybe to $200,000 lesser inventory, that's always a good thing, don't you think? Yeah. So this is not about other things, about risking expiry or whatnot. This is about operations in the process. So the lower the work in progress inventory, it tends to be better. But sometimes you don't want to reduce too much until you don't have anything going, and then that is bad. Okay? So that's more for the inventory part, right? So another, just one more example that just flashed through my mind. Inventory, you have inventory as well, right? Because if I'm giving you today 10 questions of calculations and essays and whatnot, right? So various questions to as your homework. Please, after class, go back and do, be submitted next week, right? So straight away, you have a work in progress right now. So throughout the next 7 days, you will be attempting the 10 questions. Maybe not through one session. Maybe you try 1-2 questions. After that, another day you do another, right? So if you do that, then throughout the flow time of 7 days, you will have various questions in several stages of completion. Some you might try and couldn't get it, and you think through again. Some you have written a short paragraph, don't feel good about it, then rewrite, right? So in various stages of completion, and those 10 questions are your work in progress inventory. You are the resource, right? You are the machine or the human to answer the questions. So again, that is also work in progress. Right? Okay. Um, yeah, I think that's all for these slides. Thank you, and see you in the next session.